It's recording. It's recording. Stop. Okay, we're good.
All right, can you hear me? People in the chat. Okay, cool. I'm going to start over. All right. Can this go away?
Yeah, just swipe to the right.
Good. Okay. I'm going to read it again for those people that are watching the recording. Okay, the problem asks, the op amp shown in the amplifier circuit, figure 29, has a frequency-dependent near-ideal level 1 model with parameters. The parameters are shown as mu equals GVDM, 1,000 volts per volt. That says Ri is infinity. Ro is finite but much smaller than circuit resistors, and that says frequency of the open loop is 100 hertz. Use this model and the loop gain method discussed in class to calculate the value for the closed loop bandwidth A1 in hertz. Okay, so I do want to ask, has he talked anything about loop gain, anything like that? What are some basic parameters y'all know about op amps? First off, what type of op amp is this? Nope. There's two. Like when you look at one. Oh, perfect. Yes, but what is this one? Inverted. Everybody agree? Yeah. Cool. Has he? So. Yep. The positive end is, well, how I usually look at it is where's the positive and negative. The positive end on this one is facing. It is on the bottom section of that, but it's also tied to ground. Is that the best way to put that? It's tied to ground?
It's the side your feedback loop is connected to.
Got it. This VO. This VO is going back into the negative end, meaning it is inverted. Cool. That seems important. I'm going to, I guess, keep that on there. So this is an inverted type, okay? So has he talked about GVDM and just gain in general, and what is the gain for a inverted and non-inverting?
Yeah.
So what's the gain for a inverting? Negative what? Okay, it's a negative value, but usually there are resistor values tied to that to tell us what the actual value of GVDM is actually going to be. Okay, well, this sounds like he has not actually gone over this. GVDM for an inverting. By the way, handwriting sucks. Most of y'all know that. Literally, if you have any questions on what is actually being written, let me know. Please, just please. Okay. GVDM inverting. That's weird. Negative R2 over R1, where R2 is the one coming back from the actual the actual output or the feedback. And R2 is the stuff that's coming in from R1 is the stuff coming in from the input side. So R2 is basically whatever's tied to the VO, and whatever R1 is the other stuff on the other side. Yep. Would you agree with that?
For every inverted one, the gain, yes. The
Yep.
ideal gain. Yes.
Yep. Yes. It would be the combination of. If there was one resistor there, it'd be one. But since we have these in parallel, yes, it'd be the parallel combination of.
Wait.
So what is? So have you seen this type of literally this equation GVDM equals R over R? What has he written of the R over R? What's the top R and what's the bottom R?
R2 over R1.
That's exactly what he did in class? Okay. I understand what you're saying. The R1 is all the resistance coming in from the input. So these are in parallel. If they were in series, you would add the two. If they're in parallel now, if there's more or whatever, you would add them all together to have just one total resistance. And that would be your input resistance. The same thing with the R2. R2 would be every resistor coming back from the feedback. So if there was two resistors in series, you'd add them up. Two resistors in parallel, you add them like parallel. Does that make sense? Cool. All right. So we're going to move on to the actual stuff. But I'm going to look at my notes real quick. All right. Here we go. Okay. Has he done just redrawn circuits of op amps, like going from what is shown here to what an op amp equivalently is? Once or twice. Has he explained them at all? Great. Do you mind if I erase what I have on the thing? Sweet. Okay. Cool. So, okay. How an op amp, how you analyze an op amp is kind of like how you do superposition. So in superposition, you have two, sources. When you're trying to figure out everything with this source, you turn this one off. Same thing with the other one, okay? So we want to figure out what's going on in the feedback portion of the op amp. So we don't really care about the source at the input. So that means we'll short it. It's just the wire now. So kind of redrawing the circuit, at least starting from the left. Okay. Okay. The reason I've stopped here for a second. Well, actually, no, I haven't. Okay. About to get there. So okay, actually, here's another couple typical equations. One thing he said was near ideal, meaning we're treating this as ideal. VP equals VN. Does that look familiar? The positive end voltage equals the negative end voltage. Okay. That's not what I want to write. Okay. We agree with that? Okay. Those are just equations that are normal to op amps, ideal op amps. What's up? What's up? IP equals IN. I'm going to rewrite that. IP equals IN, which equals 0. The positive end current equals the negative end current, which is 0. It's typical op amp stuff. Okay. So I have almost fully drawn the op amp circuit. A couple things is we need to now replace the op amp with its equivalent actual circuit, which is simply this. It just makes it simpler. Correct. We don't care about the input source. And another interesting thing that we change, we add a source, which this is basically acting as the source of the feedback.
Basically representing so in an op amp, there's two sources that you're used to regulate your input to meet the output. And that's pretty much acting as that extra voltage to meet your output. That makes sense?
Say that one more time? Yeah.
So when you...
Yeah, 100%. Hello, everybody. He's going to help you.
Hello, most of you should know me by now. But okay, so an op amp looks like this weird Dorito, okay? Right here. There's a plus and a minus here, right? So the parts that is op amp is there's something called a rails on each end of them, which are basically power sources. Oh, shoot. I'm not very good at writing with an Apple Pencil. I apologize, guys. 0 here, boom, boom. Okay, so these are both also different sources here. So what these do is they regulate what's coming through the op amp to meet what you want to happen. So what that means is if you're putting in 1 volt and you want 10 volts, those sources will turn into 10 volts. But also if you put in 11 volts and you want 10 volts, those sources can also reduce it to be 10 volts. This whole thing is basically controlling your output voltage. So
that source is representing our output voltage.
Yes, the source is representing your output voltage. Erase that.
Cool. All right, cool. Did that make any sense? Basically. No, so at this point, we do not care about the input. We're simply trying to figure out what the feedback part of the circuit is. A big thing about op amps is what is the feedback? Like, op amps are used for feedback purposes and just literally just a gain of a circuit. What I mean by gain is it could either add a positive effect or a negative effect. This op amp here is having a negative effect because it's inverting. It's going to make stuff smaller. And by stuff, I mean voltage. It's going to make your voltage smaller. So this Vm is representing what's coming out after the output. So theoretically, Vm could be smaller. We don't know that exactly. This voltage here is simply symbolical. We're literally not even going to put a number in it. You'll see here in a second. I don't know if Russell has put an equation that I'm going to be referencing here shortly, but it is a good equation to live by, and we've looked at a lot of solutions, and that's in like almost every single one. So this Vm is simply representing that V out. It's like the feedback voltage. Okay. So we have that. One thing that is very important is feedback equals negative VID over VID, I believe, stands for like ideal op-amp voltage. Are you falling asleep? Falling asleep in my review right now? No. No. Negative. It's the ideal voltage over the voltage. M is just a symbolic thing. So VID over VM. That's the best way to put that. That is something that I've seen in a lot of Russell material. I don't know if he's actually given that to y'all. Has he? Anybody? Does that look familiar to anybody? All right. Write that down for sure. Okay. Well, what is VID? Okay, what is VID? VID simply just the difference in voltages of the op-amp. The input part of the op-amp. As in you see in this part here, we have the input parts of the op-amp right there. That's a horrible whatever. The 0 and the minus. 0 and the minus. The positive and the minus. So VID equals VP minus VN. That's also an equation to live by. You're not going to take notes, Phoebe? Huh? Okay. One big thing here is, do you think there's going to be any time when VP is not going to be equal 0? I don't really think so, because usually the feedback is going back into VN.
Here's my question. Y'all have op-amps on your homeworks, right?
5 of them?
So to solve those, how did y'all solve those? Because VID is a parameter, pretty much. That's like a base equation. Have you guys not seen VP minus VN in general?
Yeah.
Okay.
That's just a good equation to look at. Okay. It's literally just the difference in the voltage, the input voltages of the left half of the op-amp. Best way to put it. I didn't think that. So,
that's the only thing I can think of.
So as we talked about earlier, VP equals IP equals IN, which equals 0. Okay, so there's no current. What happens when you have no current? Technically, in terms of V equals IR, 0, so that equals 0. No volts. So technically, VP and VN are 0. But the difference is, with VN, we have the feedback of the VO. Okay, we have the feedback voltage coming from VO, so we actually do have a voltage for VP. Yeah.
So we can see.
You mean VN or VP? So, okay, this right here, this is not a connection. That is a jump. Yes, but that's not tied to ground. Because that is what we changed from the op-amp model. This is literally just an equivalent circuit. The only grounds that are tied is the one on the left, this thing here, here, and here. Those are the only time, that's the only thing tied to ground. But based on op-amp equations of the IP equals IN equals 0, we can say that our voltage for VP and VN is theoretically 0, but the difference is VN is getting feedback from VO. If you look, there's nothing tying VP and VN here, or VP and VO. So there's no feedback coming back to VP. Therefore, its voltage is still 0 based on these equations here. But VN does not have a 0 voltage because of the VO, going back to VN. Is that making sense?
Yeah.
Cool. We're going to kind of move on. Okay. That means that VID equals negative VN. What the heck does VN equal? Okay. So it's kind of hard to look at this circuit at the moment. I redrew it again after this. This is the ideal way to redraw a circuit. What I did here is the ideal. Well, if you look, there's got that weird jump. There's also stuff tied to ground in weird places. What I did is this. Anybody disagree, agree, have any questions? I feel like y'all probably have questions, but. Yeah. Yeah. That's not something we short. Don't short it. Still have it there, but it's not really something we include in our equations. We'll get to that shortly. So does anybody have any questions? Disagree, agree with what I just wrote? I'll kind of explain a little bit. This jump here, right? The only thing it's actually tied to is this node right here, which is R2 and R4. But you can it is in parallel with R1 if you like redraw the circuit like I did. Because I mean it's still, this basically moves, yeah, this moves basically right here, and it's still in the same area. It's tied to Vn and it's still tied to ground. So what I did, it looks right to me, and it helps us actually figure out what we need. Okay, like I said, VP is 0, so we don't really look at it, don't pay attention to it much at all, or anything tied to VP. So Vn, okay, well, what's the voltage then? We have resistors, we got voltages. What do you think we need to do? Anybody have any idea of what we need to do to find voltage from resistors and another voltage source? We have some combination of resistors, we have a voltage source. Bingo, voltage divider is what we're going to do. Okay, so we need to look at stuff at this Vn, okay? It's kind of weird, but we need to look at stuff from the input part here in terms of Vn. The reason for that, I'm blanking on it shortly. Ohm? Okay, why we only pay attention to the left half part of, so for like R1 and R4, do you remember what the reason is that for? As in the top of the voltage divider is going to be the R1 and R4.
Oh, yes. So, what's up, guys? Come in, take a seat. So in the original circuit, you have R2 over R1 over R4, right? So when you do voltage divider originally, right? If you do voltage divider of R2, you'll get what you lost over R2, but you won't get what's going to Vn or R1 and R4. But however, as you can see in this circuit over here, Vn is technically in parallel with R4 and R1, right? And everything in parallel has the same what? So if you figure out the voltage across R4 and R1, you figure out the voltage over Vn. Did that answer the question?
Any other got any additional questions on that? Look a little puzzled. All right, thank you. So, as what he said, we have to look at the parallel combination of R1 and R4. We need to figure out what the rest of the actual voltage is connected to Vn. Therefore, so therefore, the total resistance on bottom, R1, R4, plus R2. Questions? Here's the full op amp for people who came in a little late. I take a photo of that. Yeah.
Is it going to be recorded?
It's currently being recorded. Cool. No problemo. Okay, so this is this. So what is R1, R4 parallel? So that is substituting the values. The value for R1 is 5K. The value for R4 is 7.5K. That will equal 3K. Actually, this is a question for y'all. Do y'all want me to try to like actually put the numbers in there and solve with y'all, or do y'all just want me to give you the numbers at the end and y'all go back and solve them? R1 times R4 over R1 plus R4. It's just a parallel combination of R1 and R4. Yeah. Like. Sweet. Cool. Cool. All right. So we have that. So when you plug that back into the Vn equation, that just becomes 3K on top. Okay. And the bottom one, like I said, the parallel combination of the two becomes 3K. And that R2 right there is 12K. So 3K plus 12K, 15K. Yeah. You are correct. It's actually supposed to be Vm because we're looking at the voltage source. I want to stuff Yeah. Sorry. Thank you for showing me that. Okay, so that becomes, like I said, the bottom one become 15K, as in the R1, R4 parallel is 3 plus 12, 15. That'll equal, in decimals, 0.2 Vm. Okay. Now we need to plug that back into the ID, or what is it? What equation? What equation? The F equation, which the F equation is the feedback. Right? Yes. Nope. Oh, wait, I forgot something. VID equals negative Vn. So that is that. This VID here actually equals that's important because what is it? The VID based on the equation here where Vp is equal to 0, VID then equals negative Vn. Does that make sense? Go. R1 and R4. The reason I did that is because if you look at the original circuit, I'm gonna erase some stuff. Oh, yeah, that works. This V4 here is only tied to this node here, and the ground here. You agree with that? Cool. So when I redrew the circuit for better understanding of reading it and everything, that's what I did. I redid it to where it is still connected to that node there and ground. And when we look at that, when we redraw the circuit, R1, R4 and R1 are in parallel. You agree with me there? Yeah. No, so what I did was I'm simply just redrawing the circuit. I'm making the op-amp circuit into its ideal equivalent drawn, like the equivalent circuit. What I did here, I shorted the source here because of when we redraw op-amps, we want to do it like kind of like a superposition, where the left half, the input, we don't really care about the source, and we're trying to look for the stuff on the feedback side. The feedback side is this V out right here. This V out right here. So we only care about stuff right there. When I redraw it, there's no source on the left. Okay. And when you look at the op-amp here, this would be Vin, this would be Vp. I've kept that there symbolically. Okay. And so we kind of just take out the op-amp, we just stick it in with the op-amp model. And the difference between the two is ID, as in ID equals Vp. ID equals Vp minus Vn. Okay. Vp is 0 in this instance, and most instances y'all are going to look at, because IP equals In equals 0. That is an ideal op-amp equation. And since Vp and Vn equal each other, both of them theoretically would be 0. So Vp and Vn are 0 at the moment, but we haven't accounted for the feedback of Vo. So the Vo right here is going back into the part that is tied to Vn. As in Vn is now getting another voltage. There is a voltage being supplied to Vn, but there is nothing being tied to Vp, right? There's nothing here. There's nothing there. So there is still nothing going to Vp, therefore the voltage is still 0. Yes, as in when we redraw the circuit, yes. This is just this block here. Oh, that's not what I wanted to do. Oh, it's right there. There we go. This block here is minus the resistor, is the ideal op-amp model. Thank you. So that's what we redraw. Did that answer your question enough? Cool. What's your question? Put it. Got it. This thing? Is this it? Wait. Is this it? Yeah. Hey, how's that? How's that? Cool. Yeah. Is this on? Oh, I got to do that then. Give me 1 sec. Hey man, I want to have. Oh no. Call the notes. It's free. I don't care. Okay, whatever. Any other questions at the moment? We'll get back to where I was going. Yeah,
Just because like
it's all good.
so
No, I'm just doing everything that was on y'all's problem set, so you have a good understanding of something. Wait, what? Oh, yeah, okay, that's exactly what I had covered. Okay, cool, never mind. Yes.
let me ask this also. I'm not like that.
Cool. Who had a question? Yeah.
The
34, 3K.
that's what would be.
It's all good. It's all good. I understand. I understand. Yes, like I said, my handwriting sucks. It probably doesn't look better. I don't care. Yes. Yeah. Yes. Over the voltage divider. Well, we need to make a voltage divider of Vn with respect to Vm. Does that make sense? Yeah. Yeah, he didn't with me either.
This breakdown that you're but like I'm sure he won't ask the exact same question.
Uh-huh. So most things that I'm doing is the best way to actually figure out the op-amp question. As in, I have the equations of the VP, Vn, they equal each other. The VP or IP, In equals 0. Those are just standard op-amp questions. This is a standard feedback. Okay, cool. That's a standard feedback equation. This is a standard equation as well. Those 4 equations are standards. Those are things every op-amp is going to be. And basically all the op-amps that y'all will be giving, or be given, has VP equal to 0. That's also a standard thing you probably want to put in there. I should say mostly standard thing. Okay. Standard E, that's a Q. VP equals Vn. IP equals In equals 0. Feedback equals negative VID over Vm. For an inverted, this is for an inverting op-amp. Yeah.
The top two, the VP equals Vn and IP equals In equals 0, apply to all op-amps, not just inverting. Those are parameters. Those are rules you live by. No question. The VP equals Vn and IP equals In equals 0. That exists in the name of op-amps.
So we're going to worry about PCR. Given us a question in the process or
Yep. Yep. I understand. Literally every single, the problems y'all got, the materials y'all got are the same thing I got. So everything I have is from prior solutions and everything like that. Everything I could find that makes sense in terms of standard solutions or standard, what do you call it? Equations and stuff. What?
Also, this equation is more just to gauge where y'all are in op-amps. The next one will be more standard to what you're going to get on your exam.
Yeah, okay, this one was on a homework. This one was on our homework. The next one was on a test. Yeah, yeah. I haven't got there yet. You good? Okay. So, does everybody agree with what we've done so far? Everybody, yeah. Always the case for op-amps. These standard equations here. These equations here. The top two, standard equations. This one, inverting gain. And I'll also write this one here. What? No. If it was non-inverting, it'd be VP minus Vn. Vn minus Vp.
Oh, yeah.
All right. For those who are leaving, I'd take a photo of that real quick. A photo just quick. I got to leave. Is there any other standard equations that someone might need? Oh! Here's a couple more. Wait, okay. Photos have been taken? Cool. All right. It's recorded on HKN Teams. You should check if I'm here by the time, if we're here by the time y'all get done. It's possible. Okay. Yes, the top two are the standard. Where I have the inverting part in the parentheses, after that is inverting only. Okay, so we're here. We have VID equals negative 0.2 VM. VID over VM equals negative, well, I'm sorry, the feedback equals negative VID over VM. So we got a negative times a negative 0.2 VM over VM. So literally, feedback equals 0.2. Are we here in agreement? Bet. Cool. Okay. So the actual problem, okay, there's a lot of writing here. The actual problem is asking about to calculate the closed loop bandwidth A1. Okay. We still need a couple more equations to get to. Another one. Loop gain. Signified by T equals mu times feedback. Mu in this case was given as 100 volts per volt. Mu is the same as GVDM in this case. Okay. I don't know if that's always the case. It's literally on the paper, so I'm saying in this case. So there we go. So T equals 1,000 volts per volt times the feedback, which is, also, well, the units for feedback is volts per volt. I forgot to put that down. Volt per volt. Okay. Times 0.2 volts per volt equals 200 volts per volt. Okay. Yeah. Yeah. So, what is it? F equals negative VID. VID we already found out to be was negative. Negative times a negative equals positive. So, the equation for feedback is literally negative VID. Yeah, negative VID over VM. Okay? Based on the equation VID equals negative VN, we found VN, made it negative, made it positive. Sweet. Okay, so this equation as well, standard equation, loop gain. Loop gain, I've seen it, I think once or twice. Put that down. Mu, in this case, as what was given in the actual problem, is GVDM. It sounds like it. It's possible that you'll be finding GVDM, as in my next problem, but if it should be a part of, if you're not finding it, it should be a part of the equation, based on what I've seen. T equals mu times feedback. Mu, in this case, is the GVDM, 1,000 volts per volt. That's the open loop frequency. We'll get to that shortly. So good, so good. Okay, any other questions at the moment? Cool. Okay, like I said, another thing there. Okay, I don't know where this equation is from, but I'm going to assume, I haven't written it down, but the equation I'm about to write down, I found in his solutions. It sounds like it's probably a universal solution or universal equation. The bandwidth frequency that we are looking for, 1 plus loop gain times the open loop frequency. I got you. Sorry if I'm semi-sporadic. Yeah. FA1 It's the parameter here is what we're literally looking for. Yeah, that's just the thing. Closed loop bandwidth. Yes, thank you. The closed loop bandwidth is equal to 1 plus loop gain. Closed loop bandwidth equal to 1 plus loop gain times the open loop frequency. How I found that, the literal solutions, I would not know that any other way. Same materials y'all got, I got, so same boat. Okay, so that is equal to 1 plus 200 volts per volt times the frequency was 100 hertz. So after doing the math, bandwidth thing is 20.1 kilohertz. That's the answer. I understand. That's why I've, yeah, op amps were also the weakest for me, because when we did, when I had circuits too, our second problem sets was op amps and Thevenins and Nortons. He didn't even put an op amp on our first midterm or any midterm. We literally just did the problem set, turned it in, didn't even touch it. Well, I'm sorry, we touched op amps again, but in oscillator versions, and those have readily available equations that are more streamlined. Yeah. So VID equals negative Vn. Do you agree with me on that based on previous equations? Exactly. And if Vn equals 0.2, as in found here, VID equals negative 0.2. This was Vm, and this is Vn. Does that make sense? Here, the voltage divider. We found the voltage divider here, okay? We have the parallel combination of V1 over, and V4. I'm sorry, not V4. R1 and R4, parallel combination of that, based on here, okay? That's what's going in here. That's what we need to look for. And over the total, it's free. Over the total resistance that's going into the Vn thing. So that is R1 in parallel with R4 over R1 in parallel with R4 plus R2. Okay. And that is all multiplied by Vm because voltage divider, you need voltage to get voltage. You need that. So the only voltage we look for is Vm, and that is connected to R2 and all that stuff. That is the only voltage source we have in our circuit at the moment. Yeah. Say that one more time. Okay. Yeah. I see what you're saying. Like if you were saying there was a resistor here, is that what you're basically saying? Yeah. Okay, yeah. Well, you would add those together because they're in the same branch of series, and that would become the total resistance in that branch. And then you do the parallel of the total and R4. Does that make sense? Sweet. Cool. Any other questions on this problem? I'm going to try to move on to this problem. Yeah? We good?
Something I'd like to highlight before we move on. The approach of this problem, though, is why we really picked it, because the approach, if you ignore all the loop gain and all that stuff, the approach is how you approach any op-amp problem.
I'm literally about to do the same starting steps on the next op-amp problem that I'm about to do. So like I said, standard stuff is what is the front stuff that I highlighted earlier as I wrote down.
And if you can figure out what Vn is for this one, you can figure out what Vn is for any of them. This Vn is pretty difficult.
Yep. All right. This is the second op-amp problem that I have. These are the only two op-amp problems I have. Yeah. So this was literally a test at some point. So the op-amp, oh, anybody want to take a photo real quick? Photos? Anybody? No? Yeah. Okay. Okay, well, I'm gonna read it out. The op-amp shown in the voltage amplifier network of figure 3 has the ideal model given as Vp equals Vn, Ip equals In equals 0. Those are, like I said, standard equations. Use this model in the amplifier to calculate op-amp open loop voltage GVDM in volts per volt and the op amp open loop bandwidth, okay, so those are bandwidth, those are not frequencies, the bandwidth, open loop bandwidth, F open loop, in hertz, and produce a gain error, GE, of negative 0.01% and a closed loop bandwidth of 750 kilohertz. A lot of information. Biggest thing is we're solving for this, this, and this. No, we're not. We're not solving for that. Give me a sec. We do need to solve for this. We do need to solve for this. And we do need to solve for this. This is given. That's given. The gain error is also given. We need to we only need to solve two things. Never mind my first statement. It is given, but with the two givens, as in the GVD, what is it? I'm sorry, the gain error, we will be able to find the two other things. Okay. All right. Okay. Based on what we just did, as in the first op amp, what should we do first? Okay. What do we need to write it into? Bingo. Bingo. What do we do with this? What do we do with that? Okay. What is it? Does anybody else agree? We all agree? Sweet. Yes. It is a minus. Bingo. Okay. It's an inverting. Cool. What do we do with the EG source? Turn it off because we are doing basically what? Bingo. Bingo. All right, cool. Now you've seen another op-amp prop. See, standard stuff. Standard stuff. Hopefully, doing what I'm about to do in terms of the standard stuff will get y'all some points. I don't know. I'm not the grader. Y'all know the grader, and that's y'all. All right. There we go. Okay. So, ideal model. That's a horrible position. Nope, that was wrong. We agree? Disagree? Comments, concerns, questions? I got you. I got you. Take a photo real quick. All right. So like we said, we're going to short EG because we're acting like we're doing superposition to an op amp. Okay. The ideal model for an op amp has the V in right here, VP right there. Okay. We agree? Okay. When we take out the op amp, I still have that V in and the VP tied to the same nodes they are. We agree with that? We have VP tied to this node, VN tied to this node. When I redrew it, I did the same thing. We agree. Cool. Now remember, we have to add, I shouldn't say add, we have to replace, I guess add is the better way to put it. Add the VM to our model to represent the output voltage of the entire op amp. So this VM is representing the voltage coming from here tied to ground. Okay, so what I did, that's the first thing you should, well, I shouldn't say first thing, that should be one of the first things you should do. So remember with our equations, and I'm going to start writing on some other stuff. VP equals VN equals 0. Agree? No, wait, actually, I don't agree with that. Do we agree with that? Bet. Cool. I was testing you. IP equals I in equals what? Hey, there we go. Okay. What does VID equal? I like that one better. Okay. What is VP? Bet. What is VN? I don't know. We'll figure that out. I agree. Okay. Another kind of sucky circuit looking at, I should say sucky circuit to look at. It's kind of confusing in some instances. If you want to make it simpler for yourself, you could. I do, so I will. So we need the top part, right, to have the two resistors. Okay. Tied to that node. Tied to VN. Wait. No, never mind. Give me a sec. I'm going to write it, and then I'm going to try to explain it. Well, that works. That works. Yeah. Oh, yeah, I agree with that, actually. Okay. I will explain myself. I write that right. I did. Okay. Okay. Reason I did that. What would you say R1 and R3 are in? Series, parallel, series? Cool. Did you know that because I wrote it or because you got it? I bet. Cool, cool. Yes, I got you. So those are in series. There's a node here that, what is it, VP is attached to. On the left half, it's attached to R3, and in the right half, it's attached to R4. Same thing with VN, where on the left half, it's R1, right half, it's R2. You look here, VN, right half R1, left half R1, I'm sorry, left half R1, right half R2, left half R1, right half R2. That should be a 3, and that should be an R4. And this VP node is tied to the R3 on the left, R4 on the right, and R3 and R4 are in series. Are we in agreement? Any questions of what I did? No? Sweet. Okay. So what is VN? Okay. We need to do another what? I agree with you there. What is being voltage divided? Anybody have any idea? I agree with the R1 and R3. So this is another kind of pattern recognition. On the first one we did, the stuff that was on the top was the stuff tied to VN on the left. Agree with that? Okay. Tied with VN on the left. And the stuff on the bottom was the total resistance connected to VN. VP is kind of just floating / it doesn't exist anymore because, like we said, VP equals 0 for that equation and the next. Yeah. And R2. In this case, because we have that R2 there. Yeah. So like Phoenix said, R1 plus R3, R1, R2, R3, R4, all times V. Okay. So the values for everything. Sorry. Now, in the other circuit, I just understand what you're saying because it's tied to VP. Is that why you're confused? Okay. Tied to VP here, like we said, we shorted it. We shorted it. There's nothing there. Kind of basically a wash. Tied to stuff here, you can't really get rid of it. Now, there might not be any voltage here. Doesn't mean there's not any voltage there. Do you agree with me there?
The reason there's no voltage node between R4 and the voltage source is the ground.
We in agreement? Cool. All right. So the what do you call it? Values. R1, 2K. R3, 1K. So 1K, I'm sorry, 2K, 1K. R2 is 3K, and R4 is 2K, giving us a total, when we do the voltage division, I should say the calculations, negative 0. Give me 1 sec, actually. 375 Vm. I shouldn't say negative. We'll just do this for right now. Okay? You want me to actually put the numbers in there, or are we good with the actual? Cool, cool. Okay. Now, VID, negative of what we just found. Negative 0.375 Vm. Are we in agreement? Cool. What is feedback? What's feedback? Perfect. What's our VID? Well, remember we have to have that negative outside, like you said, because it's negative. Negative 0.375 times Vm, all over Vm. Cancel, cancel, negatives cancel. F equals 0.375. Okay, are we in agreement? Everything we have done so far is what we did at the beginning of the first problem. So like I said, standard procedures is what we just did. Cool. All right. So no clue where this equation came from, but I found it. I would write it down. G of E, as in the gain error, equals negative 100%. Now this is probably explicitly for inverting. The only reason I say that is there's a negative there, and I don't explicitly know what it would be for non-inverting, but I know for this one, it's that. Negative 100% over 1 plus feedback times GVDM. Okay? Gain error. Is that what you're saying? Got it. Gain error. Okay. We were given a gain error, weren't we? The question, it said it was negative 0.01%. That is all equal to negative 0.01%. So in this equation, what is the only unknown? I agree with him. So rework the equation to find GVDM. Okay, so that negative, oh, this is negative, by the way, that's negative. Negative 0.01 times 1 plus F GVDM equals negative 100%. Are we in agreement? I just multiplied this over there. Cool. Now we just divide it out. So 1 plus F GVDM equals negative 100% over negative 0.01%. And that value equals 10K. I think it would technically be 10K volts per volt. I'm not fully sure on the, I think it'd be volts per volt, yeah. Because we're looking, this is what, that's gain error over that. I'm pretty sure that's volts per volt, okay. Now, you know, we do F GVDM equals, what's 10K minus 1? 9999. Okay. So now, GVDM equals 9999 over F. F we found earlier has to be 0.375. Therefore, GVDM equals 26.664 K volts per volt. I'll write that K a little bit better. You agree? Cool. All right, next thing is we got to find the open loop bandwidth, right? We were given the closed loop bandwidth, 750K hertz. So another equation, I don't know if this was in the materials that y'all found. A couple other people recognized this equation. This is not something I fully recognize, but this is something I found. It was this. What is it? Open loop bandwidth is closed loop bandwidth over 1 plus F GVDM. Cool? That's the equation. I'll write that down. That's, remember, open loop, open loop. This is for open loop, and it's an inverting. I don't know if it's different for an open loop non-inverting. So for this specific example, this is what I shouldn't say specific, but for open loop and an inverting op-amp, that's what the equation is. Literally, almost all the materials I found, it was inverting. So my assumption is he's going to give you an inverting. Yeah, what were you going to say? You're good. Yes. Yes. Yep. Open loop, closed loop. Okay. Plug it in the values. I don't want to. Open loop when you plug in all the numbers comes to 75 hertz. I'm gonna do this. Open loop, 75 hertz. When you plug in all the numbers. A closed loop being 750, 1 plus 0.37. Oh, well, I should say this. 750K, 1, 0.375, and that 26K, that'll equal that number. Okay. Any questions, comments, concerns? F is feedback. Anybody else? These are the only two. Yeah. Okay. Say that one more time. So technically, VI is what we solved for. Okay. But what we solved for earlier, based on the equations we're given for, like in non-inverting and actually, based on these equations here, the VP equals VN and IP, that stuff. Okay. We found that VID equals VP VN, another equation, another standard equation. VID simply equals negative VP, or VN, sorry. VID equals negative VN. That is because VP equals 0. Okay. So we then just need, what? Yeah, you can do that. Yeah. Okay. You're talking about like when you do the voltage divider. Yeah, you can put the negative there. Yeah. Yeah. Cool. Any other questions? Cool. All right. So how are we feeling? Are we feeling any better on op amps? Okay. This one? Given. Yes. Any other questions on op amps? Do we actually feel a little bit better on op amps? Okay. Okay. Yeah, that's probably my best advice. Yeah, yep. That's the best way to put it. So I hope this helps on op amps. It sounds like it's helping a little bit. So I really hope for y'all get an inverting op amp. If y'all do not, sorry. I assume Russell is not that crazy. He's not freaking other things. So I think Russell will be a little bit better and have, an inverting op amp. What? Yeah. Alm's going to speak.
For non-inverting, your gain.
Wait, write it down there a little bit.
There you go.
Okay.
Your gain would be 1 plus R2 over R1. How do you write like this? So uncomfortable. 1 plus R2 over R1. That's for your non-inverting. So if you have that gain, everything else kind of works the same. It's up for VID. Oh, shoot. Hold on. I'm struggling up here. VN minus VP. Because what the first one is your reference point, and the second one is where your error goes in for the equation. That's why they flip. Let me explain that using the picture. I see a lot of confusion. So zooming in here, right? So your feedback loop, what it's doing is it's regulating the op amp. So it's checking what's happening and going, that's correct, or you messed up, try again. And how much you mess up is based on how much information comes back through the feedback loop, how much voltage comes back through the feedback loop. Okay? So what this VID, what this equation is doing is it's basically the comparison between what you sent in your initial signal versus what your feedback loop sent back to you. And so what you get as VID is how much correction there needs to be done. So that's why it's flipped for non-inverting. Good? Oh, the G equals 1 plus R2 over R1. That's the gain for non-inverting. It's the gain if the plus is on top, if the feedback loop is connected to the plus. So if the feedback loop was connected, so instead of that whole thing, if it was connected down here to over here, R2, that would be a non-inverting.
Usually how they do that is it's usually still the same topology, but these two signs here are usually flipped. As in the plus is right here and the minus is right there. That's usually how they do it. They don't usually have the topology like this. It's usually the same arms and stuff, but the topology is usually just plus right here and a minus right there. So that would indicate as in the feedback is going into the positive when it would be a non-inverting. Does that make sense? All right, cool. All right, I'm going to take a short break. I'm going to go use the restroom real quick. I'll put this on mute for a sec. I should be back literally in like a minute. I'll be back. Cool. All right. So we're going to get back to more problems. I have, let's see how many I have left. 1, 2. I think I have 5 left. That's what I have. Okay. So,
But these will be much.
yeah, well, yeah. Okay. So let's read this. I'll zoom in a little bit. Take photos if you need. This will look very familiar. Is this the first one? I don't think it was. Oh, it's whatever. Okay. The zero state network shown in figure 1 is driven by a current source JGFT under zero state conditions. All initial conditions are 0. You are asked to do the following. Derive the time domain ordinary differential equations for the conductor voltage V4. Express the ODE in the usual form of that. And then B is calculate the undamped natural frequency, omega m, and the damping ratio, sorry. Damping ratio. Describe the nature of response, i.e. overdamped, critically damped, underdamped, or oscillatory. Go your work, well, whatever. Problem. Okay, so what do we think we're going to do on this problem? I agree. I agree with that. What's another thing we're going to use? Name, Kramer's rule, all things we're going to use. Okay. Let me pull this up real quick. Give me 1 sec. All right. So I'm not going to redraw anything. What is the admittance for a capacitor in the S domain? Perfect. What is the admittance of an inductor and what he said? Okay. So, yeah. So we use the name. All right. I'm going to start writing. Y'all got any other questions? Let me know. How we feel on name and main? Yeah. So we're using name. So we're using admittances. So we're using name. Name involves admittances. So we therefore are using admittance. Admittance of a capacitor is SC. Admittance of an inductor is 1 over SL. We agree? Cool. Do we need to take a photo or anything at the moment? You want me to zoom in more? Cool. All right. I'm going to start doing name. So first thing, okay, everybody, are we pretty confident on name and main? Okay, cool. We'll just go from there. So I do everything really large, so we're just going to do that. So everything going into node 1, SC1 plus G2 plus 1 over SL3. Are we in agreement? Being shared between V and 1 and 2 is, well, negative G2, negative 1 over SL3. We agree? Same thing down here. We agree? Okay. Stuff going into VN2, G2 plus 1 over SL3 plus just G4. Okay. What's going into VN1? And everything's in S domain. Everything's in S domain. I don't want to write the sources in S domain, but y'all figure that out. The opposite diagonals, yes. I basically just, I keep everything, so it's a negative G2 minus a 1 over SL. That also is negative parentheses. Yeah, this is also equal to. That's the same thing. Okay. Going into VN1 is J, G. Remember, we're in the S domain. So S. Would you agree? Cool. What's going into VN2 is beta I1 of S. Is there anything else? Anything else? How are we looking? Any other questions on this? Cool. What is I1? Yep. I'm going to put the inductance first. You agree? All right. I'm going to write just this matrix first, and then we'll add everything together. So that'll become, I'm going to separate also into independent and dependent. Oh, also, what's beta? Beta is given as 2. Write that a little bit bigger. Okay. J of S, 0 plus 0. SC1, VN1. That is also equal to JG of S, 0 plus 0, 0, SC1, 0, VN1, VN2. We agree? Thank you. So we don't agree. Okay, cool. All right. Subtracting that from our normal matrix would be very similar. SC1 plus G2 plus 1 over SL3 minus G2 minus 1 over SL3 negative G2 minus 1 over SL3. Remember, we subtract this stuff This becomes minus beta SC1. This becomes G2, 1 over SL3 plus G4. Vn1, Vn2 equals Jg of S. Are we in agreement? Great. Okay. Cool. When you plug in the values, you'll get this. 2s plus 2 plus 2 over s. Okay. So when we plug in the values for this here, we get 2s plus 2 over s. When we plug in the values here, we will get negative 2 over s. We're good? We plug in the values to the left bottom, this, we will get negative 2 minus 2 over s minus 4s. Okay? And when we plug in the values for here, we will get 6 plus 2s. 2 over s, I'm sorry, 2 over s. 6 plus 2 over s. If you have any questions, just let me know. Okay? Yeah. This? Okay. I transformed this matrix, the current matrix, I'd say dependent current matrix, to an independent current matrix and a, admittance matrix multiplied by a voltage vector to get the same thing. I took the voltages out of that matrix and made a whole new matrix. Yep. And then I have the Vn vector multiplied by the admittance matrix, which is this. Basically, these two multiplied equals this. Does that make sense? Yeah. So, the matrix multiplication, how it works is it's this times this and this times that. Okay? That's the first part. And then when you get to the bottom, it's this times this and this times this. So, if I were to do this times this and this times this, I'd get the same thing here. As in would it be plus or minus if I do this and this and then this and this? Would the 0 times Vn of 2, would that be added or subtracted to Vn? It'd be added. Yeah, it'd be added. Yeah. No, that'd be added. So if I were to take this matrix and go back here, this times this plus this times this would get me 0, which I have. And this times this plus this times this would get me that. So I just broke apart the matrix to get that. Does that make sense? Making more sense? Sweet. So, and when I broke this apart, I then subtracted it from that matrix to get us nothing changes in these 3 parts because there's nothing in those 3 parts. But the only thing that changes is I subtract this, that term there, by, I subtract it by beta SC1. Because I'm trying to subtract it over, combine like terms in the equation. Then the equation looks like that. Does that make sense? And when I look at the, when I plug in the values, I get that. Cool? Wait. So, we're going to move over to our best friend. What's our best friend? Bingo. Okay. So, like it said, it wants V4. Well, what is V4? What is V4 in reference to nodal voltages? Perfect. It's V2. I agree. V4 of S equals Vn2 of S. Well, what does Vn2 of S equal in terms of Kramer? Okay. Yeah, I agree. I'll write it down a little differently. The -1, 1 plus 2 times delta 1, 2 over delta times j g of s. So exactly what Phoenix said, just a little bit different. Yeah. So Vn2, okay, Vn2 is denoted as, why do we, I think that'd be more of a math question. How I've always looked at it is just that's what we do for Vn2 is look at delta 1, 2. So as in, we have the current in the first node, but we're looking at the second node. So the current, and okay, cool. Learn something new. Yeah. Yeah. Exactly. Exactly. And I think if the source was over here, it'd be delta 2, 1, delta 2, 2. If we had a source right here, when we look at Vn1, it'd be 2 delta 2, 1 for Vn1, and if it was Vn2, it'd be delta 2, 2. So if this one there, we had this, we were looking for Vn1, what do you call it, the delta thing, I plus j, or Vn1 would just be, nope, there we go. 1, nope, 2 plus 1 times delta 2, 1 over delta. The reason why it's 2 plus 1 is when we do the when we do Kramer's, it's -1 to the I plus j. I represents this number, and j represents that number. Yeah. Using terms I don't use. Sorry, I don't know to turn it off.
No, no, it's not. So that -1, that's a math thing. It's factor expand. Basically how you break down a matrix and take that and take. Kramer's rule is just taking a section at a time. So that's actually a math thing. That's not a. That's correct. The -1's on the other.
Have y'all done that and gotten correct results? Okay, that's perfectly fine. That is something I've never done before, never heard of that. If it works for y'all, sweet. This one works for me. It'll be a little bit different, but this is all symbolic. It'll all figure out here shortly. So like I said, yeah. Say that one more time. Yes. I kind of get what you're saying. It's hard for me to visualize. Say that one more time. Thevenin's is MAME, and you find a current source. Norton's is MAME, and you find a voltage source. Did that? Okay. And we were trying to find Vn1 or Vn2? Vn2? If that's just a thing we're adding, no. If we had the original one here, if this was still here, but we had a J0, no, we would use this. We would use the delta 1, 2 over delta if we were using Vn2. So so for Thevenin's and Norton's, the stuff we add, we don't take that into account to our Kramer stuff. You just simply do the thing that's already existing. The thing where you account for the JO and stuff is in the final equations and final calculations. Cool.
Also, Josh, I have a better explanation on why
Cool. Do y'all need a little bit more explanation on that or no? Cool. Oh,
I'm gonna basically completely ignore this problem for a second to explain this.
yeah.
Let me just go down here really quick. So just the basic circuit real quick. You have hold on. There we go. Here, let's just say here to here, and then this circuit here to here. Okay. So this is point 1, point 2, 1 prime, 2 prime. Okay. So how our matrices is set up once we have that is you have, I'm just going to call them S because S parameters are very common in this kind of thing. But you have S11, S12, wait, no, sorry. S21, S12, and S22. Right? My diagonals? Yeah, okay. So basically what those are saying, those positions when you do Kramer rules, is what it's saying is it's starting at, I'm going to go laser pointer for this. So it's starting at the first node and it's coming back down to the first node. So it's the resistance between the top part of the first node and the second one. It was, okay. Okay. Dang it, I knew I was right the first time. Yep, you're right. But, so it's basically saying that starting at the first one, going back to the second one. Okay? So then S21 is you're starting at the first one and then going across to the second one. So what's in that spot in that matrix? Or sorry, S12. Starting at the first one, going to the second one. Keep messing that up. But what's that saying is that's the resistance between point 1 and point 2 when you're transferring it across. Okay? It is. That's what these parameters mean. So S21 is basically going the other direction. So if you start at 2 and going to 1, what's the resistance in the middle? And then S22 is from the second node down to the second bottom part of the second node. By the way, these things right here, 1 and 1 prime, are called terminals, pretty much. Okay?
We'll actually learn this later on.
Yeah.
What he's doing.
Yeah. But that's why I use what you do when you do Kramers. Did that answer everyone's questions? You said kinda. What's up? Yes. So. Mm-hmm. Yeah. Yeah, that's pretty much what it is. Perfect. Josh, you're up again. Oh, you don't have to circle?
I mean, I do, but that's already less stuff.
Here you go.
Thank you. We are doing, do y'all want to look at the original problem? Basically, we're trying to find damping ratio. Cool. And mega N. Cool. Cool. That's the original answer or question. So. Cool. Cool, cool, cool. All right. Cool. You good, Brian? Cool. All right. We did the name, did the, what is it, transform of that, or transform of this, I should say, to nodal voltages. Have the matrices, have a final matrix, and symbolically have it with numbers. And we're doing Kramers. Like I said, Kramers is great. Whoop, whoop, whoop. Okay. So, -1, 1 plus 2 of delta 1, 2 equals, knock out the first row, the first column, or second column, first row, second column, that is left. First row, second column, that is left. If it was delta 1, 1, first row, first column, that is what is left. If it was delta 2, 1, second row, first column, that is what's left. If it was delta 2, 2, second row, second column, that is what's left. So what we are doing is delta 1, 2, that is what's left. That makes sense. Cool. All right. And it's negative. There's a negative being multiplied because it's, oh, that's negative. It's supposed to be inside the parentheses. -1 to the 1 plus 2 becomes -1 to the third. What's -1 to the third? Bingo. So the entire delta 1, 2 is being multiplied by negative. So this negative 2 over s, negative 4s, or negative 2 minus 2 over s minus 4 of s all becomes positive, which means 2 plus 2 over s plus 4 of s. Okay? Okay. Now, my next question to y'all is, what is y'all's method to find determinants? Yeah, Inspire? Anybody else? Anybody else actually use algebra? Bet. We're using algebra, so if you're curious, keep following me. Okay. Yep. Delta. Yeah. Oh, yes, I'm sorry. Thank you. Yep. Well, I'm just trying to find what delta 1, 2 is. I'm just trying to find the top part. I'll do the multiply JG of s here in a little bit. But I'm explicitly just trying to find this right now. So I don't need the JG of s yet, but thank you. So that'll be, the determinant, that times that minus that times that. Okay, that is, yeah. Home can. I always was the dude who wanted to write everything out. Just my brain made it simple. There were certain times I write fast. But yes, there was, okay, a lot of his numbers on the tests are relatively simpler than like 500 microhenries or microfarads, something like that. Like he literally has these, look at the numbers here. This is a test problem. 2 500 milli, which 1 over 500 milli is 2 over s, or 2 over 1, whatever. And then 4. So they're simpler numbers. They're simpler numbers. So yeah. That is what I like to do, so I'm going to do what I like to do for those who are interested. All right, so like I said, that times that minus that times that. Okay, so 2s plus 2 plus 2 over s, okay, times the next term, or I should say times this term, which is 6 plus 2 over s, all subtracted by these two terms. And I like to write this one first. That's just me. Negative 2 s, nope, negative 2 minus negative 2 over s times negative 2 minus 2s minus 4 of s. And remember, this is still negative in the actual determinant. It's still negative because we haven't changed anything actually here. The reason why it's positive here is because in the numerator, it's multiplied by this negative 1 to the third. So that means the entire numerator, as in delta 1, 1, will be multiplied by a negative. Does that make sense, everybody? All right. Algebra. All right. 2s times 6, 12s, plus 2s times 2 over s. Now, what I like to do in terms of, what do you call it? When I'm multiplying something s times something over s, I like to keep my s's. I don't like to cancel them out. It just it helps me mathematically later, and I'll show you that here in a little bit. So this will become 2s times 2 over s, which will just become 4s over s. So now we'll do 2 times 6, 12. 2 times 2 over s, 4 over s. That's a plus. Now we have 2 over s times 6, 12 over s. 2 over s times 2 over s becomes 4 over s squared. Agree? Now I like to put the stuff that I do here, I like to put that down here, so it's just easier for my brain to track. So it'll be all negative. Negative 2 times negative 2 equals 4. Negative 2 times negative 2, this should be over s. That's a 2 again. There we go. Negative 2 times negative 2 over s becomes positive 4 over s. Okay. Oh my God. Negative 2 times a negative 4 over s becomes positive 8s. Agree? Negative 2 over s times negative 2 equals positive 4 over s. Negative 2 times negative 2 over s, both of them, becomes 4 over s squared. And negative 2s times a negative 4s becomes positive, that's a square, positive 8 S over S. Okay? Another reason I like to do this, right? You see you got, these are all negative, these are all positive. Well, you have a negative 4 over S and a positive 4 over S. They cancel each other out. You have a 4 over S and a negative 4 over S. Cancel out. You have a, what else you got? What else you got? Yeah, that's just 12. You got other stuff, but I'm going to distribute the negative and then do actual, a little bit more math. So the top part, the parts from there that are still left over, 12S plus 4S over S plus 12 over S. That's from the top part. This is all subtracted by 4 minus 4 over S minus 8S minus 8S over S. Okay, Matt? Do you agree? Do you agree? Yeah. What do you mean by factor out the S's? I see what you're saying. Yeah, Russell and I, what is it? I just do something different than Russell. What I do is I distribute out the S's later. You could do them earlier if you wanted to. Perfectly fine. I just do them later. I would try to do it. So combine like terms. We have a negative, or we have a 12S minus 8S. That just becomes 4S. We have a 4S over S minus an 8S over S. That just becomes negative 4S over S. We have a positive 12, negative 4. That then just becomes positive 8. And then we have 12 over S minus 4 over S. Then becomes 8 over S. Are we in agreement? Are we in agreement? Give me one sec. I think I did something wrong. Let me track my work. Okay. Oh, I did just cancel them out. Okay. Okay, cool. All right. So I have these numbers. Okay, that's what I have. No, I understand. Just I'm looking at something. Earlier, I literally said I don't cancel out the S's, but I'm looking at my work and I canceled out the S's for certain parts. So I'm like, what am I doing? You know what? Might as well. Those cancel out. And that just becomes 4 over S minus 4 plus 8 over S, which just becomes 4S plus 4 plus 8 over S. Cool. Sorry about my confusion there just a second ago. You can do whatever y'all want to do, as in cancel out the S's like I did here, or you can't. I literally think that I might have done both in this session, but I actually did. So that's just my brain scattered, but whatever. Plus, I got you. 4S plus 4 plus 8 over S. Sorry. Cool. That's our determinant. So V4 of S equals the numerator, which will be 2 plus 2 over S plus 4S all over 4S plus 4 plus 8 over S, all times JG of S. Agree? It's just whatever. Wait, how does it look like you mean like an upside down in? I don't care. Okay, fine, whatever. So, do you all understand it? Enough? Thank you. All right, so what do we do now? We want to try to get what we have done so far into this equation here. What do we do? What do we do? Off of what we've done, what do we do? Yep. So V4 of S equals 2S plus 2 plus 4S squared all over 4S squared plus 4S plus 8 times JG of S. Just for my brain, I'm going to rearrange some stuff real quick. 4 over S squared plus 2S plus 2 all over 4S squared plus 4S plus 8 times JG of S. My brain likes that. What do we do now? What we do now? We simplify? Is that what people are saying? So we have to get to this form here. Okay? How do we get to what we have to there? So I have V4 equals a numerator over denominator. Everything has S's all multiplied by JG of S. Yeah. Well, no, you can do both. Well, you have to do it for both. Okay. I agree. I agree. So V4 of S equals 4 over 4 S squared. 2 over 4 is, yep, 1/2 S plus 1/2 S squared plus S plus, it's supposed to be an 8, so 2. We agree? Wait. Okay, what do we do? Oh, wait. You shouldn't have agreed. There we go. Okay, cool. All right, what do we do now? What does that 4 over 4 become? Cool. What do we do now? I wouldn't say divide. We want to move. We want to have V4 times a lot of stuff equals a lot of, or V4 times a lot of stuff equals JG times a lot of stuff. So therefore, we multiply the denominator over to the other side. This is exactly like, I'm pretty sure, your first problem on y'all's thingamabobber problem set. All right. Okay. There we go. Okay. What do we do now? We can do a couple things. Depends on the order, I'll say. We're in the S domain. What do we want to be? The what domain? I thought you said I for a second. Yes, time. Okay, I agree. So what do we do? Well, do y'all want to go to the time domain first, or do y'all want to distribute? Distribute the V4s and distribute the JGs. Sorry? Want to distribute? Anybody else? Anybody care? Distribute? Cool. So the way I'm going to do this is we have the, what is it? The derivatives, the voltage, and then the coefficient. Oh, I'm sorry. The way he has it is the coefficients, the derivatives, and the voltage. So what I'm going to do that exact thing, except we don't have derivatives yet because we're still in the S domain. So I have S squared V4 of S plus S V4 of S plus 2 V4 of S. You agree on the left side? Yay? Nay? All right, next one, S squared JG of S plus 1/2 S JG of S plus 1/2 JG of S. We agree? Cool. All right, now, Laplace transform. D squared dt V4 of t plus d dt V4 of t plus 2 V4 of t d squared d, oh no, d squared dt squared jg of s plus 1/2 d dt. Oh, that shouldn't be of s. Oh, whoopsies. T jg of t plus 1/2 jg of t. Okay. So do we agree with everything I've said so far? Okay. So what he wants us to look for, okay, we have it in this form. Cool. We've done part A. Yay, 20 points. Woo. Okay. Now the next thing Natural frequencies and damping ratio, however you say that, whatever. Okay, how do we find those? We have this form here where we kind of have like, I wouldn't say a polynomial, but it is a polynomial technically in the S-plane. We got A1s, we got A2s, we got S's, S squared. Thank you. Sorry, what do we do? Hey, does anybody remember this formula? Say that one more time. You're close, and that's also the equation for zeta, as in the damping ratio. Okay. No. I'm just looking for omega so far. Omega in, as in our undamped natural frequencies. This is the equation. What is our A1? Based on this equation. We have this number, which is 1, this number, and this number. Here we go. Bingo! 2. Okay, what units are is omega in? Units. Radians. Radians per meters. I like that one. Radians per second. Okay. Zeta. That's how I'm going to write it. I'm pretty sure how Russell writes it. I'm pretty sure it's just a cursive Z. What's that? There's technically 2 formulas. We've already solved for something, so I would just use the one with that. I assume none of y'all remember it because you don't remember the first one. A2, okay, cool. I like the way we started. You're missing one thing. He's more right than you. Bingo. What's A2? What's A2? Bingo. Which that equals. Okay. Okay, I'm going to write my 5s a little bit better. What's up? Yeah, I got it. No. Actually, I will double check just because you said that, but 90% sure it's. Yeah, it's just A2. So, another thing he mentioned, nature of response. Overdamped, critically damped, underdamped, oscillatory. We got 4 things I'm just going to tell you what zeta could be. Based on the number that we are given, is it overdamped? I'm sorry, I'm going to say this better. Is it undamped, underdamped, critically damped, or overdamped? I agree with that statement. Why do you say that, though? Perfect. We agree? Sweet. All right. Any questions on this problem before I move on? That's literally what you do. If he gives you stuff in, he might give you a thing where it's MAME. See if that's what I have later. There you go. What is MAME? An oscillatory circuit, okay, what he described, right, says overdamped, critically damped, underdamped, and oscillatory. And what I said of underdamped, overdamped, critically damped, and undamped, underdamped, critically damped, and overdamped. What are the 3 things that we both said, and what are the 1 things that we differed? I didn't say oscillatory. He didn't say what? I said undamped, underdamped, critically damped, overdamped. I disagree. Wait, no, actually, I do agree. I do agree. Whoopsie. Okay, yeah, because undamped meaning the circuit can do anything, as in there's nothing stopping it from oscillating. Does that make sense? No, when zeta is 0. As in undamped, there's. I got you. Also, if you get an imaginary number, what he gives you, this, you did something wrong. Can you all read what I'm writing? Okay. Got any questions? Let me know. Rules to live by there. Can I move on? Still right. Looks like we're still right. We've gone through 3. I have a total of 7. So I got 4 more, but I got an hour. Of what I have, I still have to cover 2 more topics. Do you want me to just cover one of those each? I believe I have 2 problems for this type and 2 problems for open circuit and short circuit natural frequencies. Do you just want me to can the other 2? Huh? That's fine. That's fine. Yeah. So I've done 2 op amps. I did 1 of the system specs. The next one I have going, open circuit and short circuit natural frequencies. Do we want to do this one? Or, got it? Or do we want to do this one? Yep. They're asking for the same things. They're just different problems. It's asking for the natural frequencies, open and short circuit. They're both asking the same things. Which one do y'all want to do? This one, I will say this. This one will require name. The other one is neither. KVL, KCL. You want to do the one that I'm currently looking at? Okay. Sweet. Okay, that's fine with me. Okay. All right. KVL, KCL. Okay. What's KVL? I'm sorry. What's KCL? Cool. What does it mean? All the currents going into a node equals what? Currents leaving it. Okay, what's KVL? I wouldn't say mesh. Well, yeah, around a loop. Yeah, I guess that's equal to 0. Yeah. Cool. So we have current IA. Let me read the problem. A zero-state network shown in figure 2 uses a voltage-controlled voltage source as an active element. Use the component values as given to calculate the range of our transconductance, GM. So basically, we have this GM here. Oh, we weren't given a value. We're going to use things to find GV, or GM, I'm sorry. And those things are our open circuit and short circuit natural frequencies. But what we're doing that is we will find the transconductance for when the open circuit natural frequencies lie on the left half of the S-plane. List these frequencies clearly to clearly indicate that they are on the left half plane or in the left half plane. And I should say, the open circuit natural frequencies that lie inside the right half of the S-plane or on the j omega axis, whatever. We'll say S-plane. List these frequencies clearly to indicate they are on the right half or that they are just in the right half of the j omega as well. So what does it mean for something to be on the left half of the S-plane? Okay, I agree with the stable, but what else? Like our poles have to be what values for it to be on the left half plane / stable? Negative. I agree with that. So on the right half plane, for them to be on the right half plane, they'd have to be, if left half's negative, right half plane is what? Positive. That means it is unstable. Perfect. Okay. So I know it says ZDP of S, and that tells us that we have that. I don't like that. I'm going to be honest. Well, there's two reasons. One, because the way Russell did it made sense in my head, and he doesn't use, what is it, ZDP? He actually uses YDP as an admittance driving point admittance, whatever you want to say. So we'll be in the S plane, meaning we'll need to use, like I just said, admittances. So we'll, at this point, we have a current, right? We have a current IA. Current IA is going to equal the total transconductance, I'm sorry, total conductance, not transconductance, sorry, times our total voltage. Do you agree with my statement? Yeah, conductance. Yeah. That's IA. I'll write that better. Sorry. I'm glad he asked. Huh? IA is the current shown here. I agree. I said conductance. Technically, in this term, it'd be admittance because we have components that are imaginary, meaning we need conductance plus acceptance, which is admittance. Okay. What is the stuff, as in, what is our total admittance and our total voltages? Okay. So let me do KVL, KCL. IA equals going to L1, that's as LI, L1, plus the current going to C2, plus the current going to, I'll just put 1 over R3 to make it G3. I don't want to rewrite stuff on the actual circuit. So I'm just going to say 1 over G3, 1 over R3 to make it G3. 1 over R3. And the total current going into the branch of this one. Current would be the same for both those resistors in the branch, correct? Since the two resistors are in series, the current for both of the resistors will be the same because they're in series. If they were in parallel, the current would be different, but the voltage would be the same. Are we in agreement? Sweet. All right. So I'll just say that branch. What do I want to call it? I'll just do this. Now, if we were to turn this into like a G total, like a total, I should say, total inductance, we'd have to add them together in series and then flip them. Do you agree with me on that? As in, we'll call this GR4 has to equal R4 plus R5. You take the inverse of it. We agree? No? Why not? We agree? Yeah. Well, that's basically what I'm doing. As in, I'm saying the current of this branch here is the current of that branch here is just saying this. That's this and this are the same thing. You agree? Yeah. This? This? There we go. So that is to denote V5, and V5 is important because it's part of the dependent source. Yeah, it's just some parameters. So, okay. Now, GM times V5, what is that? I should say, what is this source? A current source. Okay, cool. And it is going what direction? Yep, it's going up. What is the direction of IA? IA is going that way, that's going that way. Meaning they are either opposed or agreeing. Which one? Opposed. Therefore, what do we do here? Bingo! We agree? Wait. All right. Now what the heck is V5 of S? What's V5 of S? How do we find that? Voltage divider. Thank you. Cool. All right. And so for voltage divisions, I want to keep it in resistances. So this is going to get it kind of confusing where we're going from resistances to conductance, blah, 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 blah. But what is the voltage divider for that R5? What did you say? You said R5 over. I agree, but what? Yep. And then why is it EG of S? Yeah, cool. Voltage in the parallel, is that what you said? Yes, exactly. As in, the voltage here is the same as the voltage here. I agree. There we go. All right, cool. So then we can substitute. What's up? We're keeping this one in resistances. It's kind of weird. The reason I did that, okay, the reason I kept this one in resistances, doing a current, well, I guess if I would have done a voltage divider in admittance, it would have been the admittance of the thing we don't. Well, that'd be just kind of weird. It'd be a little weirder. 4 times. Yeah. So do that. Okay. So what is the current of L1? What is the current of L1? This thing here. What is that current? Well, what's our voltage and what's our admittance? Yep. Yes. Okay. So IA equals EG of S times 1 over S L1. What's the same thing on I2? EG of S times SC2. The reason why it's SC2 and it's 1 over SL1 is because we're in admittances, meaning admittance of an inductor, 1 over SL, admittance of a capacitor is CL? SC, I like that one. All right, cool. Now, what is what is the current in that this branch in terms of admittance times voltage? Yep, I'm going to keep it a 1 over R3 though, just for math's sake. I don't want to have to redo math. That's S. I'm going to shrink this a little bit, sorry. I want more space. Now we need the voltage here, or we need the current here. EG of S times 1 over, oh, that shouldn't say R4. That should not say R4. That should say R3. R4 plus R5, because when we find the total conductance in that branch, it's R4 over R5 to find the total impedance, and flip it for admittance. You agree with that? Okay. And then the last one, wrong sign. Minus EG of S times R5 over R4 plus R5. Okay, do y'all see a similarity between each term? Yep. Okay. Nope, that shouldn't be like that. Is GM1. GM is not given. They're trying to look for values of GM. What we're looking for is we're looking for values of GM where our open circuit natural frequencies will be on the left half of the S-plane, and our open circuit natural frequencies would lie on the right half of the S-plane. Steps will be very similar to done before. Frequencies, step will be very, very similar. And stuff will be a little. Everybody agree with what I'm doing so far? That. This term here was cut off a little bit, but it is just this. R5 over R1, R4 plus R5, because we found the voltage divider here for V5. And the reason that is the case, so if you look, I forgot a term. Let me scrunch some stuff. Okay, so in this equation, I went from all the currents to doing voltage times admittance. But if we have this term here, right, I still need to have that GM. Then I have the voltage times the admittance, voltage times admittance of V5. Does that make sense? I understand what you're saying. So this right here, okay, that's a conductance times a voltage to get a current. Okay. Oh, I got you. Yep. But yeah, I added the term there, as in I multiplied it. I kind of forgot it a second ago. And the reason it's here, we basically are trying to get, well, this and this would technically cancel each other out in terms of it's a resistance over a conductance. I should say it's a resistance over conductance. Yeah. 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 Cool. So R4 plus R5, because I'm right here. And then the last part is minus GM R5 over R4 plus R5. We agree? Cool. What do people think we need to do now? What do y'all think we need to do now? We could do a couple things, but I'm just curious. Oh, wait. We have stuff in currents. Like I said, so when y'all find open circuit and short circuit natural frequencies, what is the thing you set it equal to? Like you have short circuit natural frequencies and open circuit natural frequencies in a fraction, or the other way around as an open circuit and short circuit on bottom, but those are usually equal to what? Those are also equivalent. Those are called, I wouldn't say ZG, I'd call it driving point impedance or driving point admittance. So usually, like in everything y'all done in the problem sets, y'all found either your driving point impedance or driving point admittance, and you then had for a driving point impedance, you had your short circuit natural frequencies on top and open circuit natural frequencies on bottom. Yeah. Yes, it is, but it's not supposed to be. 5. Sorry. Did you say? I heard you say. Okay. But do y'all agree with what I'm saying? Driving point impedance, you will find your short circuit natural frequencies on the numerator and your open circuit natural frequencies on the denominator. Do y'all agree with that? Do you know why? I got you. For driving point impedance, you will find your short circuit natural frequencies on the top. Short circuit natural frequencies on the top of the fraction. Yep. Z equals short circuit frequencies. I got you. Give me 1 sec. So for impedance, okay. So impedance equals, that's PD, it's supposed to be DP, equals V over R, right? Nope, 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 nope. Yep, okay. Okay, when voltage is 0, what is happening in the circuit? When a voltage is 0, which a wire is essentially a short circuit. So you find your short circuit natural frequencies in the numerator because when your numerator is 0, as in for your voltage is 0, you would have a short circuit. Yep. And the why it's in the numerator, when current is 0, okay, as in, when current is 0, what do you have? Open circuit. And what is that in terms of impedance? Is it 0? Is it a value? Is it maybe infinity? Exactly. Exactly. So a short circuit, I'm sorry, an open circuit is when impedance is literally infinity because nothing's touching, as in that's the general theory of that. So when current is equal to 0, our impedance will equal infinity, as in when current is equal to 0, we have an open circuit. Therefore, open circuit natural frequencies is on the bottom. Does that make any more sense? Huh? For impedance. So this is how I remember this. So this is this for impedance. What's admittance? Bingo. Literally just do that. So that is how I remember that. So does that make more sense? Sweet. Thank you. I found that in my circuits too all by myself. Probably not, but whatever. All right, cool. We're here. So we can do a couple things. What I'm going to do next is I'm going to normalize everything, as in no S's on the bottom. So this is all one term. Oh, wait. I literally was going to do something that I didn't do. Okay. Why I'm doing YDP? What is current over voltage? Current over voltage is perfect. So if you divide this over, you will get Y dP equals 1 over, I'm just going to copy paste this. I should have done that all along. iPads, woo, nice. Okay, now I'm going to normalize some stuff. Whoa. So this is all one term. So if you do that, YDP equals, I'll do this, 1 over L1 plus S squared C2 plus S over R3 plus S over R4 plus R5 minus GM, I'll put an S right there, S times GM R5 over R4 plus R5 all over S. Y'all see a couple things we could do, make stuff similar. At this point, you could also just plug it in a calculator. There's a lot of stuff to do, but the way I'm going to do it is I'm going to combine a couple like terms and make my life a little bit simpler. Oh wow, that's there. Okay. Okay. Cool. So I'm going to make my life a little bit simpler by doing this. There. YDP equals still the same. L1 plus L, S squared C2 plus SR3, S times 1 minus GM R5 all over R4 plus R5. And this is still all over S. The reason I did that, R4 and R5, there's two terms here, have the same denominator, so we can add them together. So that'd be an S minus an S, GM R5. Took out the S, so I got an S times 1 minus GM R5, R5 plus R5. Oh, I'm sorry, R4 plus R5 on the denominator. Does that make sense? Cool, cool. That should be a plus right there. That should be a plus. Cool. Well, I guess I should have done this to begin with. I can do that even better. Do 1 over L1 plus S squared C2. You know what? Nope, no, we're going to keep doing it. Plus S times 1 over R3 plus 1 minus GM R5 over R4 plus R5 over S. Am I doing this the most efficient way possible? I don't think so, but I'm doing it a little bit efficiently. So now, for my brain, I am going to put stuff into S squareds, S, and whatever. So S squared C2 plus S 1 over R3 plus 1 minus GM R5 over R4 plus R5 plus 1 over L1 over S. We agree? Yeah. So 1 over L1, I had a 1 over S L1 by the admittance of this inductor. The admittance of that inductor was multiplied by our total voltage to get our current of our voltage, which is coming out of this node. Okay? Because IA equals the current going out of that node for KCL. Okay? So I then took all the EG terms out, factored out, and then I still have a 1 over SL1. Did some stuff with the YDP as an I over EG gives us YDP. Still 1 over SL1. To get that by outside, as in normalize it, I should say not outside, but to get rid of that 1 over S, normalized it as multiplying the entire equation by S over S, which is equivalent to 1. Agree with that? Cool. And that got rid of the S tied to that 1 over S, or that got rid of the S of the 1 over SL1, just leaving us with 1 over SL1. On the denominator. So like the biggest thing is all these problems there might be there might be a number with a 1 over S in something. But the way we want stuff, we do not want an S in the denominator. So therefore, we try to normalize it as in multiplying the equation by 1 or S over S to get rid of that S in the denominator by doing this. If it's just 1 over S L1, that is one term. That is one term. That's the same as just saying like 2. Because we could plug in a value for S and we'd get a term. We'd get 1 over, like, if S was like 2, we'd get 1 over 2 times whatever L2 is, which would be 4. Or I'm going to just say 2. So it would be 1 over 2 times 2, which would be 4, which would just give us a number of 0.25. Did I say that weirdly? So this is just one term. But to get rid of the S, we would make it the times S over S. Therefore, that would cancel out. We'd have 1 over L1 divided by S. Now, this S over here is fine because we want a numerator and a denominator. But the terms in the numerators and the terms in the denominators, we do not want to have fractions in. Does that make sense? So this whole thing is the numerator of this number, and this whole thing, well, I should say, if you were to look here, we have 1, we just have a value equals another value. No denominator, no numerator, there's just something equals something. You agree with me on that, right? This part here. YDP equals this big number here, but theoretically, if you put values in, it could just be all one number. Does that make any sense? In one second. Oh, got it. So the S over S is there to just get rid of this fraction number here. Because we have in our numerator, we have in our number a number. We have in our big number a smaller number that's a fraction that we don't like because currently we're not actually putting in a value for S. If we were to, this would just become a big number. Am I confusing you? I feel like I might even be confusing myself. Okay. But so this S over S just cancels out this S right here, like I saw here. So we got this 1 over L. Okay. So we did here, what we got here, S squared times C2 plus S, that term, plus 1 over L, all over by S, okay? Well, we have something multiplied by our S squared term. So what do you think we need to do? Bingo. Nope, wrong thing. Nope. One over L1, sorry. No, that should just be, let's do this, let's that. Okay. Do we agree with what I did? I got the C2, I factored it out. So I had to divide by a C2 here, because if I was to, and here, because if I was to factor that back in, that just becomes C2S over C2, giving us back the S. Same thing here, or if I were to multiply this C2 back in, it would become C2 over L1 times C2. C2s would cancel out, and I'd be left with that. That makes sense? Wait. Okay. Now we can put in some numbers if we want. Actually, we're going to put in some numbers. So when you put in numbers for the values that are listed above, that 2 microhenries, 500 nanofarads, 1K, 300, 200. Okay. What we eventually get as our overall function is this. 500, 10 to the negative 9, all times, I'll just do this one now, S squared minus 800 times 10 to the third times GM minus 7.5 times 10 to the negative third. That's all multiplied by S. Plus 100 times 10 to the ninth. That is all divided by S. Okay. We have this term here. Okay. I'm sorry. We have, standard polynomial thing in the numerator where we have S squared plus A2S plus A1. Got that? Sorry. But give me one sec. It is in our numerator, meaning our numerator of our YDP will be our what frequencies? Bingo. And is that what we're looking for? Indeed. Okay. So, give me one sec. Okay. Find this next part again. Thing where we did the polynomial extension. Oh yeah, I'm gonna friggin' no, I don't wanna buy it. No. Remember, okay, so based on something I found, or based on his solutions and stuff, we determined that to find out where where the GM will lie, either on the left or the right half plane, we simply just have to look at this value here. And that value there, A2, that is A2 in terms of our, S squared plus, that's a horrible writing, but you get what I'm saying. Has to be, A2 has to be less than 0 for left half plane, and A2 has to be greater than 0 on right half plane. Yeah. But for the explanation, give it a front.
So this is just to make sure you're on the right track for this stuff. So when you're factoring two things, right? Let's say you have A minus B and then A plus C, right? What do you think your signs are going to end up in the finals? What? Well, there's a little factoring thing that'll help you check real quick. That's why. So this becomes A squared plus AC minus BA. Minus BC. Yeah, there's a bad example. Hold on. Bad example.
I think I actually woke up home from his house.
Yeah, I'm very much so out of it right now. But okay, sorry about that. So if you have A plus B and A plus B, comes out to A squared plus 2AB plus B squared, right? If you have A minus B, you get A squared minus 2AB plus B squared. Agreed? So what do you guys notice about the signs in those polynomials? So this second sign, if it's positive, it tells you both of the factors. You can see, right? both of the factors will have the same sign. And if that's positive, then this first sign will tell you what that sign is. So that's a quick trick you can use. Is that all you want me to explain? Okay, yeah.
So that is why
Sorry.
we're explicitly looking for A2, because in the term of the polynomial, A2 would be this whole term here, and that whole term there. So if if they're both positive, like you see here, A and B, the zeros of this formula would be negative B, 2 negative B, correct? As in you have, like, you know, A has to equal negative B for stuff to be 0, right? Same thing here, except backwards, where A has to be positive B to stuff for stuff to equal to 0. So therefore, when we look at A2, we are determining where our poles, because for open circuit natural frequencies, there we're looking at the poles, we are determining where they will be. Because if they're negative, like they are here, they'll be on the left. If they're negative, or if they're positive, like they are here, they'll be on the right, as in our poles. Does that make sense? That makes sense. Okay, cool. Are y'all cool if I erase this part? Or this part? Are y'all cool if I erase that part? So, like I said, for A2, or sorry, for I flipped it. My bad. I flipped it. The reason that is the case is what I just said a second ago. As in, if this is the case, if A2 is 0, we'll have a term where it's an S plus A, okay? If this number here turns out to be positive, we have an S plus A, okay? And that'll mean that our two poles, negative A, meaning both of them are on the left half plane. Are we in agreement? And if we had S minus A, both of the poles would be positive on right half plane. Does that make sense? Yep. So that's why for the left half plane, we will need A2 to be greater, and for the right half plane, we will need A2 to be less. Because if it becomes this, I'm sorry. That's positive. This will be that one. Does that make sense? If this is the same as S plus A, which is the same as saying, or which means our zeros will lie, or what is it? When stuff is equal to 0, it'll be negative A, meaning on left half plane. If it's this, yeah. Yeah. So yeah, like when you separate your polynomial into your two functions, right? What are those called? What is this called? It'd be something factors. Thank you. When you separate the polynomials to your factors, to find the 0 of that factor, you just take the inverse of whatever this number is, right? So if S is negative A, it becomes negative A plus A, which this would just turn out to be 0. Same thing here, turn out to be 0. And that's for this thing here, when we find our zeros of the numerator for YDP, it's actually our open circuit natural frequencies. Does that make sense? Did I confuse anybody? Yes. Yes. Well, so remember, we weren't given a value at all. We just want to see a value. We just want to see when stuff, we just want to see when our open circuit natural frequencies will lie on the S half plane when GM is whatever value. So we want to see what GM equals or is less than or greater than to have our open circuit natural frequencies on the left or the right half plane. Exactly, because that's what we're about to fall. That is exactly what we're about to find. Dang, I just keep getting put in. Right. There we go. Okay, so that means, so for A2, which would be this whole thing, remember you include the negative, this has to be greater than 0 for left half plane. Then it has to be less than 0 for right half plane. Okay. So I'm going to do this one first. Okay. And that's the case. You just divide over that negative 800, whatever. So that just becomes Gm minus 7.5 times 10 to the negative third is greater than 0. So that means that Gm has to be greater than 7.5 times 10 to the negative third. And Gm is a conductance, so just be in Siemens. Does that make sense? Yep. 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 And so what is it? We solve for Gm, so then for G, that is left half plane. Gm has to be less than that for it to be right half plane. Does that make any sense? All right, cool. When he means second sign, he means this.
That's a negative.
Yep. Okay. So I'll move on and do one more problem. Sorry. Any other questions for this one, I should say? I know it's we've been here for a minute. Yeah. Yeah, so okay. So poles and zeros refer to when a part of a fraction is 0. Zeros is when the Yes. I agree. But if you have a fraction where it's zeros on the denominator, it's going to be undefined. That's what I meant. Exactly. Exactly. So poles and zeros for impedance, driving point impedance, and driving point admittance are flip-flopped. As in zeros for zeros. What is it? For driving point impedance equals zeros, poles, which equal short and open. For dependent, you still have zeros and poles, but they're equal to open and short. Does that make sense? What? Okay. Okay. So does that make sense? Good? Anybody have more questions on this problem? Okay, we good? Okay, nay? I got one more. We'll try to get out of here. I'll try to do a little bit faster. Yeah. Actually, we have 14, whatever. Okay, so I have this one here, which we'll do MAME to find our, it says Y trans, or what is it, transimpedance, transadmittance, but it's basically saying YDP. We'll have that one. Or I have That one. Is that it? Okay, my bad. That's the only one I got. No. As in, I mean, okay. Do y'all want to do one more problem or do y'all want to leave? Because it's essentially doing the same thing. It's essentially doing the same thing, and you just find your, what do we need to find? We just find our YDP, basically. Open circuit natural frequency. Yeah. Technically, this is one more. This one technically covers your, try to pull up your problem. System specs was the zeta and undamped natural frequencies. 7 is the Nortons. We basically have done this to find our open circuit and short circuit natural frequencies. So we do this to find our open circuit and short circuit natural frequencies. So in the open circuit and short circuit natural frequencies, we just go a little bit more in depth. Does anybody need another one? This is MAME. We haven't done NAME. I'm sorry. All the ones that we have done, I've done NAME. This one's MAME. If you want me to do that, I'm perfectly fine. If you want to leave, perfectly fine with that too.
How about this? This one's crowd participation.
I mean, that would probably be longer.
Okay.
Someone say something?
Y'all just want to set it up.
Everybody feel like they're all right? Works for me. All right, cool. Well, I guess I'm going to end the thing here. Thanks for coming, and good luck on your test. Yeah, thank you.